some example. Now we are going for the discussion of non-deterministic finite automata. So we are going for this, and we understand this as NFA. So non-deterministic finite automata is NFA. Okay, so here now I'm going to tell you the key points, right, by which you have to go for remember this every time, and so that every time your non-deterministic finite automata will be correct. Okay, so key pointers. Key pointers. Uh, First point is understand uh, your regular expression. Okay, understand your what instead of your we can say um, uh, understand the supplied regular expression. Okay, supplied regular expression. Okay, so means what we uh, need to produce or prepare a set of words. Now you can ask me why, because we can check these words by using your finite automata, preferably non-deterministic finite automata. Means your non-deterministic finite automata, if it prepares the same sort of word as that of the regular expression, then it is correct. Okay, so means you may have okay, so this means one more important thing. This tells me that um, you may have you may have uh, you may have many representation. You may have many representation for what? You may have many representation for a same problem. Okay, uh, same problem uh, same problem of RE. So you may have a various representation for same problem of RE. The only thing is that their correctness is ensured on the basis of words. So the correctness is being only ensured on the basis of words. So the key pointer, this is first point. This is important, and this is first point, that you need to understand the supplied RE. We need to produce and oblique prepare the set of words. Why it is? It is because that you can check the word by using NFA, and you may have many representations. So it means that, like, if you are being asked to draw a non-deterministic finite structure for one regular expression and you drawn it, and your friend has drawn a different structure, so there is a confusion that you have drawn this structure and your friend has got a different structure, then which one is correct? So for checking it, you need to just ensure that whether it prepares the same sort of word as that of the regular expression or not. This is important. Okay, now the second most important key pointer is that you need to allow, or you can draw uh, epsilon transition states, right? You can draw epsilon transition state. Okay, and do not hesitate in drawing the epsilon transition. So because whenever at the end of the day, whenever you are trying to convert, whenever you are trying to minimize the epsilon states and converting that NFA structure into a deterministic finite automata structure, there you'll find that your automata is going correct. Okay, so don't hesitate, don't hesitate in adding epsilon structure. Now I will let you know, like, where you can add the epsilon state, right? So there is no such rule is being, but as a matter of practice, uh, you can decide like where the states are being added. So you start adding the epsilon transitions. So these are the two key pointers which you need to understand. Okay, so let us try to work with example number 1. A simple example will say you have a language L. Language L is defined by set of input alphabet A only, and such that you have a regular expression A star. Okay, and you are asked to uh, draw NFA, right? You need to prepare a NFA, non-deterministic finite automata, for this. And already we have seen the basis, like how it works, what are the important points that. So let us try to go with this particular key pointers. What is being asked to me is that, okay, if I have been supplied with a regular expression like this, I need to prepare the set of words, and for me the set of words include epsilon. Then I need to have one A. Sorry, I need to have one A. So I need to have A. I need to have two A's. I need to have three A's. So many, so forth. I can go for A raised to n, such that where n goes from 0 to infinity. Okay, so means my non-deterministic finite automata must produce me epsilon. Okay, so let us try to understand this, how it can be done. Okay, so and the next important point is that my whatever the NFA structure that I am going to draw, this must satisfy these words. This must satisfy these particular words. So let us try to understand this now. How it can be like. Just go ahead with this now, drawing a non-deterministic automata. So simple case, let's go for this. This is my zeroth state. Then this is my state number one. Okay, so I'm going with epsilon. Then 0, 1 to 2, I'm going with A input, and from this I'm going to 3 with the same input, and this is going to be my accepting state. Okay, but in order to get epsilon, if I follow this particular path, my output will be at this, it will be epsilon A epsilon, right, which means it is giving me A. Okay, but I need epsilon here. So what I will do, okay, I am going from this to this now with epsilon. Okay, so means if I and for this A, my path is 0, 1, 2, and 3. Okay, now but for getting epsilon, my path will be 0, 1, and 3. If I use 0, 1, 3, I'm going to get epsilon here. Okay, but what if I wanted to have AAs? Okay, so do I have AAs here? Now look at here. So 0 to 1 with epsilon, 1 to 2 with epsilon I'm getting. Now, but to have one more, is what I'm going to have. I'm going to jump from 2 to 1 with epsilon input so that I can have one more. So here I can say that I'm going for 0, 1, 1 to 2, 2 to 1, 1 to 2, and 2 to 3. So means, see, look at here, 0 to 1, 1 to 2. So 0, so I'm going with 0 to 1, 1 to 2, 2 to again back to 1, again 2. So this is 2 A's and this epsilon. So this is how I can go for. Now if I wanted to have A raised to 3 in this case, in this case, what the path will be 0, 1 to 2 to 1, right? So to 2 to 1 to 2 to 3. Got it? So this is how you can prepare for this. Now let us try to have one more example. That is example number 2 here. So let's say this is 2. So you have a language L which is based on set of alphabets sigma, such that it contains A only, and being defined by A plus. Now being defined by A plus, then what is going to be the regular expression, finite non-deterministic finite automata for this. So here I'm going to draw the structure like on the same ground as that of the uh, A star. So this is 1. So this is 2, and this is 3. So this is epsilon, this is A, this is epsilon. Okay, so and this is going to be my accepting state. Okay, so look at here. So what is this? If it goes with epsilon A epsilon, which means if I go with epsilon A epsilon, it means I am going to get A. Okay, so for this A plus, my set of words are WR A A A, so many, so forth, A raised to N, where N goes from 1 to infinity. Fine, so this is how it works. So, okay, but now, okay, let's go for this one. Now I want two A's to be generated. Now for this, the path which is going to be followed is 0, 1, 2, and 3. Okay, but now for AA, what is the path? Do we have a path? So okay, so 0, 1, 2. Oh, I want one more A. So for having one more A, I'm going back here. This is epsilon. Okay, so now let us look at here. So 0, 1, 2, one more A, 2, 3. So it is say 0, 1, 2, 1, 2, 3. Okay, now can I have three A's? Okay, yes, I can have 0, 1, 2, 1, 2, 1, 2, and 3. Okay, so this is how you can prepare. Now, what is important point? Let me tell you important point with respect to this using some different color so that you can understand here in much better way. And this is important is so important point I'm going to write here. Important. Okay, important is where you uh, add epsilon states. Where you add epsilon states. So you look at here. If this is multiple closures, this is multiple closure before 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 the closure and after the closure it is being prepared. Okay, so it's a general practice. Before closure and after closure it is being prepared. So where you can add it before and after closures. Okay, where you can add this before and after closures. Okay, so